and as long as it is 3 millimeters thick plus or minus the specified tolerance, the sheet passes. But what if during the process of moving the floating ribbon of molten glass, a subtle disturbance is introduced to the molten metal? Let's say this disturbance imparts a 1/4 of a millimeter wave-like undulation throughout the entire ribbon. Now to the eye, the cut sheets would appear flat and they would pass quality checks for thickness, but the surface of those sheets of glass are far from flat. Flatness isn't derived from how closely a part matches its specified dimensions. It's a property completely independent of the part's gross shape. Parts can be made completely dimensionally compliant, yet still lack flatness on its features. Because of this, the flatness of a surface is specified independently of other dimensions. If we take a surface and sandwich it between two imaginary parallel planes, the gap between the planes that encompass the surface is known as a tolerance zone. The distance between planes in this tolerance zone is how flatness is specified. The smaller this distance, the flatter the specification. If the surface's irregularities can't fit within the tolerance zone, it's not flat enough for the specification. Flatness is in effect the difference between the highest and lowest point of a surface and its relationship to a specified tolerance zone. It is possible to force flatness on a surface without explicitly specifying it by tightening the dimensional tolerances of a part. For example, if we made the thickness tolerance of our float glass to be plus or minus 0.1 millimeters, it would cause the sheets affected by the undulations to be rejected during quality control. However, this practice can create dimensional specifications that may be impractical or cost prohibitive to meet for some parts. Much like float glass, many objects appear to be flat because of their dimensional tolerance, but are actually not designed explicitly to be flat. A flat wooden tabletop, for example, may vary up to several millimeters, yet still fit its specified tolerances. Even a large, polished, granite kitchen countertop, generally known for being a flat, solid surface, can vary up to 0.03 of a millimeter along its surface. On parts that do explicitly define flatness, the method of both measuring and producing flatness is determined by how tight of a tolerance zone is required. Adding to this, some specifications may even specify a maximum allowed change per area of surface, preventing abrupt changes to the overall flatness of the entire surface. Flatness specifications down to around 10 microns or about 4/10,000ths of an inch are quite common in machinery. Found predominantly on part mating surfaces, at these tolerances, traditional milling can be used. For larger faces, tooling designed for milling flat faces such as face mills and fly cutters are common. Those mating and sealing surfaces found in car engines can be found at this level of flatness. Sealing in fluids at this level of flatness require the use of a gasket. A gasket is a mechanical seal which fills the space between mating surfaces while under compression. Gaskets allow for less than perfect mating surfaces on machine parts where they can fill irregularities. They are usually made out of compressible materials such as paper, rubber, silicone, or metal. Field testing flatness at this level is done with a known precise flat edge and the clearance probing tools such as feeler gauges. The flat edge is placed at several positions spanning the surface to be tested, and the feeler gauge at or above a maximum allowed deviation from flatness is used to probe the clearance between the surface and the flat edge, offering a simple part usability flatness test. Actually measuring the flatness of a surface is a lot more complicated. An obvious solution would be to measure the surface against a flat reference. For example, if a part has a surface parallel to the surface to be measured, it could be placed on a surface plate. A surface plate is a flat plate used as the main horizontal reference plane for precision inspection. A height gauge can be used to probe the top of the surface for flatness relative to the surface plate. However, the problem with this method is that you're really only testing how parallel the surface is to the surface plate and not actually testing for flatness. Furthermore, not every part can be fixtured in this method. Because flatness is a property that's independent of other dimensions, it must be measured in a similar manner. If we first place the part to be measured upon 3 columns with adjustable heights, then with a height gauge, run the probe along the surface while looking at the amplitude of the probe needle, we get a snapshot of the differences between the highest and lowest point on that surface. We then adjust the 3 columns to minimize the amplitude of the needle. The goal is to adjust the orientation of the plane in order to come up with the smallest difference between the high and low spots on the surface. This smallest possible range of travel is the measure of the flatness of our surface. In effect, we're reconstructing the tolerance zone sandwich of the surface. Measuring flatness manually requires significant training and experience, and it can be a very tedious procedure. Automating the process with the use of a coordinate measuring machine or a CMM is a common practice. A CMM is a device that measures the geometry of a physical object by sensing discrete points on the surface of the object with a probe. CMMs are typically computer-controlled and can be programmed to perform the tedious, repetitive measurements needed to determine surface flatness. The probe is programmed to sample the location of the surface within the CMM's working space at numerous points. The resulting data, known as a point cloud, is then processed through an algorithm known as the minimum zone method. Two theoretical planes are calculated that best sandwich the point cloud, effectively determining the allowance zone of the surface. Because the aligning of the surface is done in software, measuring flatness with a CMM can be done very efficiently with minimum fixturing. CMMs are generally accurate down to about 2.5 microns or 1/10,000th of an inch, making them ideal for use with milled flat surfaces. Going beyond the 10 micron level of flatness requires the use of surface grinding. It's a widely used abrasive machining process in which a spinning wheel covered in rough particles cut chips of metallic or non-metallic substances from a workpiece, making it flat. Grinding is commonly used on cast iron and various types of steel. These materials lend themselves to grinding because they can be held by the magnetic chuck commonly used on grinding machines, and they do not melt into the wheel, clogging it and preventing it from cutting. Surface grinders can easily produce flat finishes down to about 2 microns of surface variance. This process is typically used to produce precision parts, precision fixtures, measurement equipment, and tooling. Similar to grinding, face honing is a process in which a large working wheel with a thin layer of abrasive is used to grind workpieces held in a carrier disc. Face honing allows for the grinding of multiple small parts at once and is commonly used for ceramic tooling inserts, watch windows, LED wafers, bearing rings, gears, cutting knives, and carbide tooling. When extremely flat surfaces are required beyond what grinding is capable of, lapping is used. Lapping is the process of rubbing two surfaces together with an abrasive between them in order to remove material in a highly controlled manner. In lapping, a softer material known as a lap is charged with an abrasive. The lap is then used to cut a harder material. The abrasive embeds within the softer material which holds it and permits it to score across and cut the harder working material. Lapping can be used on a range of materials from metals to ceramics and glasses, and at its limit can produce surfaces that vary by only 30 nanometers or about the height of 300 hydrogen atoms. It can be performed by specialized machines or by hand, and the process can accommodate sizes from tiny handheld parts all the way up to large optical pieces found in telescopes that can take months to produce. A curious phenomenon that occurs when surface flatness approaches 1/10 of a micron is called ringing. Ringing is the sliding of two ultra-flat faces together so that their faces lightly bond. When wrung, the faces will adhere tightly to each other, requiring a significant amount of force to separate them. The exact mechanism of why this occurs is unknown, though it's believed that molecular attraction starts to occur when the two very flat surfaces are brought into contact. As flatness gets into the nanometer scale, the force-reducing effects of surface roughness are removed and full contact bonding actually becomes possible purely by intermolecule forces such as van der Waals forces, hydrogen bonds, and dipole interactions. This technique is used in an optics manufacturing process known as optical contact bonding. Measuring the incredibly small surface variances at this level of flatness are near impossible to do with direct surface contact, so optical methods are used. In order to accomplish this, the interference pattern created by light reflecting off the surface to be measured is used. This is done by using a special precisely polished flat lens known as an optical flat and a monochromatic light source of a known wavelength. Common sources are low pressure sodium lamps or a helium neon laser. When an optical flat's polished surface is placed in contact with the surface to be tested, dark and light bands are formed when viewed with monochromatic light. These bands are known as interference fringes, and their shape gives a visual representation of the flatness of the surface being tested. The surface flatness is indicated by the amount of curve and spacing between the interference fringes. If an imaginary line is run through the optical flat, each band of curved interference fringe it intersects represents a half wavelength of variance in the surface at that region. For example, if the light source has a wavelength of 600 nanometers and the imaginary line intersects 3 bands, the surface flatness for that area varies by 900 nanometers. Furthermore, the direction of the curves represent if the surface is concave or convex. Straight, parallel, and evenly spaced interference fringes indicate that the work surface flatness is equal to or higher than that of the reference surface. Some optical flats can even create band divisions anywhere from 1/4 of a wavelength down to 1/20th of a wavelength, allowing for flatness resolution down to about 30 nanometers. Both grinding and lapping can be used to achieve a subtly different property of surfaces known as surface roughness. Surface roughness, like flatness, is based off the peaks and valleys of a surface. Surface roughness, however, measures how much the average of a surface's variance deviates from the intended surface. Surface roughness can also be specified for any shape, not just flat surfaces. In general, surface roughness specifications are far smaller than those for flatness. They typically exist in the submicron range, but as flatness variance approaches extremely small levels, the two properties may begin to converge. Perfect flatness near or at one atom of variance are possible but are beyond the scope of mechanical means. At these levels, mechanical flatness give way to chemical deposition and thin film technologies. Direct manipulation of atoms with scanning tunneling microscopes can even achieve perfect surfaces by manipulating them one atom at a time. At these scales, the definition of flatness quickly becomes moot.
Here's why most people lose money as a stock trader. Manipulation. That's the problem.
Okay, class. So I think only have a 15 minutes. So I just want to just summarize what is the flatness and the straightness according to the video that I shown just now. So I think just very brief on the topics today. Right. So
Doctor,
yes,
doctor, from my view, the screen is really blurred.
really blue, really.
Right, yeah.
My God. So is it all of you or only Mahesh? How is it
Same.
supposed to be? Same. Alamak. How's this?
Blurred
Internet
also.
connection. Okay, okay. Let me stop sharing first. Then I will share it. Maybe. How's it?
Now it's okay.
Yeah.
Better.
Okay. Thank you, guys. Okay. So for today, I think I cannot upload the file yet. So just a brief regarding on this because on 8:30 10:30 we will do a quiz. So for this topic, so you already know the flatness and straightness according to the video just now. So why the straightness and flatness is very important to the applications that we want to produce. For example, like gas to produce a part very flat in order to make sure that they don't have any leakage or something like that. So that is a flatness and straightness means. So for from the video also you know what is the process that you have to do in order to achieve the flatness surface of that you want to produce. At the same time, at the end of the video just now, they only come up with the surface roughness. So you can see the relationship between the surface roughness and also flatness or straightness in your application. So if the surface roughness of the surface is really high, so it will affect the flatness. So that's why the flatness and severe roughness they have interrelations each other. So you have to know how to produce a very good part according to the flatness and severe roughness. So according to the video just now, they have like a milling process, polishing. So all this process is a process to produce a very flat surface. So I will upload the slide after this. So we only have 10 minutes on that. So uh, this is the machines that we use in order to produce a part. For example, lathe machine, in order to have a turning process, and we want to produce the, the, the very good surface. So we need to know what is the machining parameters that we want to apply or to machines your parts in order to achieve a very good surface finish in terms of roughness and also flatness. All right. So basically, in this topic, is topic 4. We will discuss regarding on the straightness and flatness measurement. So you have to do, and you must understand what is mean by the straightness and what is mean by the flatness. And then topic 5, we go with the surface roughness. So from here we can see they have a roughness and roundness. So that is the topic 5. And then we complete my part getting on the meteorology part. So next we proceed with the quality control with the Dr. Ramza. So for the straightness and flatness, they have like a 2 weeks times to cover on this topic. So I think they have like an online test. I tried to do an online test, so cannot meet you guys again. Alamak. So just do a online, and hopefully we can meet on the final exam. So this is the first outcomes that you have to understand. So able to determine the straightness along a guideway using the autocollimator. So you have to know what is the mean by the autocollimator. And next, you are able to determine the flatness of the polished surface using an optical flat. So I'm not sure whether you have chance to try it. May I because now we the online mode. So I really hope that you can imagine how to do that, because you have to understand the way how the autocollimator will be operate for the measurement of the straightness, and how the optical flat will measure the flatness. So what to do? Now everything is online, so you have to know without practically apply in your application. So I will try my best to explain it with the video demonstrations or something like that. So hopefully we can have the stations. Maybe we talk to technicians, and then we can do a live on that. So hopefully we can do that. So what is the autocollimator, also you have to know the details. So this is a straight measurement using autocollimator. Okay, I think this machine already broke, broken here. I'm not sure whether they have the maintenance on that. So if you come in here also, we cannot do but I can explain it in terms of the video and how the autocollimator will make sure that your part will be do in the straight measurement. So uh okay, this is a basic principle. So I will explain it detail regarding on the autocollimator on the Thursday. So you have a 5 minutes to do a preparation. So it's a very easy quiz, and then I believe you can score maximum because multiple choice. You can tembak, so you can it's a very easy, and I really hope that you guys can score easily 5 marks on that. Okay, all right. So how many questions? So of course they have 10 questions. So it's very enough time, because uh I got a meeting on the 10:45, so that's why I cannot proceed with the class today. So I will upload the group and also the topic 4 slide by today. Inshallah, I try my best. And we meet again on Thursday. So wish you all the best and Assalamualaikum. If you have okay, don't quit yet. I still open this. So please let me know if you have any problem in order to access the e-learning. Okay, just maintain in this room. So hopefully if any questions or any problem encountered during the quiz, then you can you can ask me straight away. Okay? Right? Thank you very much. Assalamualaikum. Seronok kelas hari ni setengah